Good morning and welcome all of you to the course of Embedded Sensing Actuation and Interfacing System. So in the last class, we have started our discussion on the temperature sensor, right? So under which we have discussed about the RTD, its salient features, characteristic, followed by that the thermistor, and both of them are resistive type sensor. And after that, we have also discussed in detail about the 3-wire and 4-wire RTD configuration in order to reduce the effect of lead wire. So lead wire we illustrated. So that is the wire which we use to take out the connection from the sensor to the control room. And in that context, we told that simple 2-wire RTD is having a lot of errors in terms of its performance. So that's why they are not used in most cases. And the 3-wire RTD, where 3 leads are there, they are used in most conventional applications. And but this particular 3-wire, although it can reduce the effect of lead wire, but it cannot nullify them completely. So that's why the 4-wire RTD is there, which can completely nullify the lead wire effect, but it is relatively costly, and also it is not, and that's why it is not that much used. So this 3-wire is having in between performance, and that's why this is more popular. Then in that context also we have illustrated that how in the Wheatstone bridge the 2-wire, 3-wire, 4-wire RTD are connected, and how their performance are improved with respect to the 2-wire RTD, okay, in order to reduce the effect of lead wire. So in this context, let us take a small homework. So this simple Wheatstone bridge based circuit for 2-wire and 3-wire, please derive the output voltage expression. So a small homework, please take it. So derive V out, derive V output for this Wheatstone bridge for 2-wire and 3-wire RTD. Okay, and check how the effect of lead wire is coming into the picture in 2-wire and 3-wire. Okay, so how to solve this simple Wheatstone bridge? If we look at this simple Wheatstone bridge, the first configuration. So if here we have the voltage of 10 volt, and then what voltage should be at this node? If this is 350 ohm, this is 350 ohm, and this is grounded. So someone quickly tell me what is the voltage at this node?
5 volt.
Very good,
5.
very good, 5 volt, because voltage divider is there. So since the current, we can consider that this current is passed through this branch and this branch, and across this V output branch, ideally no current will flow. Why? Because you can consider this one as open circuit, or even if you put some voltmeter over here to measure the voltage, we consider the input impedance of the voltmeter is very high, so that no current can pass through this particular that terminal, right? So that's why we simply consider the current is passing through this one and this one. These are the two parallel branches. So at this node the voltage is 5 volt, whereas at this node, the voltage, in order to find the voltage, you have to calculate the, you have to see that here, suppose RTD you can consider 350 ohm, then this lead resistance you can consider some 5 ohm, and then this is 350 ohm. So from that you can calculate what is the output voltage. Or instead of considering R lead some value, you can just RL, both you can consider equal. This one is also RL, this one is also RL, and that's why what will be the voltage you can calculate, and you can take the difference, this 5 minus this or this minus this. From there you can calculate what is the output voltage. And then again, for this case also, again you can apply similar logic and check what is the output expression, and then try to compare that how the effect of R lead is minimized in the 3-wire configuration with respect to the 2-wire. Okay, so please all of you try this. If anyone faces any difficulties, so then in the next class you can let me know. Okay, next, Next, we discussed about these practical signal conditioning circuits for thermistor as well. And for thermistor, simply the voltage divider circuit, followed by that a simple amplifier or buffer block we have used to convert the resistance change into voltage change. And in that context, we have discussed about the self-fitting effect and how the designers need to be aware of this problem, that what are the aspects it need to take into account. That aspect also we have discussed. After that, we have discussed on this thermocouple, which will give you direct electrical output. And in that context, we have also illustrated the requirement of thermal compensation circuit. Okay, so thermal compensation circuit in order to that compensate the reference junction or cold junction temperature variation. So what we said, if the reference junction temperature gets varied somehow, which is not expected, then that will be affecting my overall output. So in order to reduce that effect, we dedicatedly use some thermal compensation circuit, which will take care of this reference junction temperature variation, and accordingly it will correct that effect. Fine. After that, we have discussed on this IC temperature sensor, which is basically manufactured by this semiconductor technology, based on the semiconductor technology, and which mostly works on the diode principle, because as you know, the current across the diode depends on the temperature, and that property is exploited to develop the IC temperature sensor. And here we have shown the diagram of LM135 series, which are manufactured by NS, that is National Semiconductor. And this is the schematic block diagram. So here you can see these 8 pins are there, and mainly the diode property is exploited. And you can see that actually this will be the current passing through this diode. So Zener diode principle is there, right? So the output you can get, current output you can get from this terminal, and if you connect some resistance, so if you connect some resistance across this pin, then from the across that resistance, it will convert that current into voltage, and that voltage will give you the measurement of the unknown temperature. Okay, so till this point, is it clear to everyone? Any doubt? I hope all of you can hear me clearly and see the screen clearly, right?
Yes, sir.
Yes, sir.
So if the temperature sensor concept is fine, so then let us move forward to the next type of sensor, which are coming under the motion sensor. Okay, so our intention, what is our intention? We are discussing. So initially we started the background on this embedded sensing, actuation and interfacing domain, their various salient features, applications and importance. And after that, we are gradually moving forward to the sensing part. So for that, we have defined what are the data sheet, how to interpret the data sheet. In order to interpret the data sheet, we need to be aware about the static and dynamic characteristics of the sensor, modeling of the sensors, that aspect. And then we started our discussion on different important sensor being used for our embedded application. Okay, and in that context, the temperature sensor we have covered, and also the salient features of each of the temperature sensors, like for RTD, thermistor, thermocouple, as well as ice temperature sensor, we have discussed, and some signal conditioning flavor also we have given, right? That for RTD or thermistor, what type of signal, basic signal conditioning scheme is required, like voltage divider or Wheatstone bridge. For thermocouple, what is the special type of signal conditioning aspect, like temperature compensation. So the basic or the salient aspects of the signal conditioning part also we have discussed. And more formally, we will be discussing on the signal conditioning part after covering this basic sensor actuators. Then we will formally start our discussion on the fundamental signal conditioning aspect, and there we can get acquainted with more fundamentals, or also we will brush up the more fundamental concept with respect to the signal conditioning. But while discussing about this individual sensor, then also we have mainly given the glimpse of the salient or special type signal conditioning circuits required for the dedicated sensor. But the general signal conditioning aspect, that we will take up after completing the sensor actuator part. Okay, so motion sensor means what? It will monitor the location of various parts in a system, and motion means what? It can give you the informations regarding position, displacement, proximity, acceleration, angular velocity, and so on. Okay. Now, principle of operation. So what we said, that sensor means always we prefer the output of the sensor should be electrical. Input can be any physical quantity, but output can be electrical. And what we iterated multiple times, that electrical quantity means either resistive or capacitive or inductive. Right? So these are the most three fundamental electrical elements. And obviously there are other special type of materials or sensors are also there, which can show you that some other properties. So they may not be directly resistive, capacitive, inductive, like piezoelectric, triboelectric. So those we will see later on. So anyway, so effectively in more conventional approach, either I can convert the physical quantity into electrical quantity either by some resistive mechanism or inductive mechanism or capacitive mechanism. Okay. So the fast motion sensor which will come into your mind is the simple potentiometer. Potentiometer is a very simple motion sensor which can be used to measure the position or displacement. And in this resistive in this potentiometer, the resistive mechanisms will be used to convert the position or displacement into voltage change. Okay. So potentiometer means you know that there is some knob is there, and effectively so this potentiometer equivalent circuit will look like this one. So suppose three terminals will be there, right? So this is terminal 1, terminal 2, terminal 3. So terminal 1 you can connect to the supply voltage, terminal 2 you can connect to the ground, and terminal 3 you can consider as the output. And terminal 3, this is actually the wiper. So here you can see this shaft is there. So if you move this shaft, if you rotate this shaft or move this shaft, then this will be sliding across the length of this potentiometer. So sliding across the length, what does it essentially means? It means the effective resistance gets changed, because here the electrical equivalent will be something like this is one resistance, this is another resistance, is not it? So if this one increases, so this one decreases, or vice versa. So from here we are taking the voltage out, is not it? So by changing this middle terminal that we call as the wiper, so by changing these wiper positions, we can effectively vary the resistance across this potentiometer. And varying the resistance means what? The output voltage will be also varying according to the resistance change, because here we have applied some supply voltage Vs. Now if these are increased, these are decreased, or vice versa, so then accordingly your V output will also change. And why? Because the voltage output is changed. This is because of the position variation of this wiper. And where from that position variation is coming? That position variation is coming from the object whose displacement or position I want to measure. So suppose if I have an object over here, and if that object is moving in this way, so simply I can connect this object to this wiper, so that when this object will be moving, accordingly this wiper will be sliding across this potentiometer length, and accordingly the output voltage will vary. And from that the output voltage we calculate, and from that output voltage we can tell what is my object displacement or object position. Okay, so this is the simple basic potentiometer which works on the resistive principle. Similarly, we have other motion sensor which works on the inductive principle, that is called as the LVDT, linear variable differential transformer. Okay, so we will illustrate in detail about the functionalities of this LVDT, but as of now you can understand this linear variable differential transformer means here the input will be displacement and output will be voltage, obviously. So the construction look like this one. This is the based on the transformer principle. So here we have one primary coil, and on the contrary of the conventional transformer, where in the conventional transformer we have one primary and one secondary, but in the case of LVDT we have one primary and two secondary, and those two secondary are connected in series opposition. So you can see this is one secondary, this is another secondary, they are connected in series opposition. So series opposition means effectively the V output you can consider as V1 minus V2. Okay, because of this connections of this two secondary coil. And in so here in this primary side we will be applying some sinusoidal voltage, AC voltage, and because of that AC voltage the flux will cut in this secondary coil, and the flux cutting will depend on what? This will depend on this core position. So you are in your first year electrical, all of you are aware about the basic transformer. So here we have the core, and depending on the core position, the flux cutting in the secondary coil will vary. If the core is towards the upper one, so then the flux cutting in the upper secondary will be more with respect to the lower one. If the core is in towards the lower position, then the flux cutting in the lower secondary will be more than the upper one, and so on. So depending on the position of this core, the flux cutting at V1 and V2 will be different. Accordingly, your output voltage will also vary. And by measuring this output voltage, we calculate what is we estimate what is the displacement. Okay, and this is the standard characteristic curve. So either you can have, so suppose if you take the mod value, so then if this is plus x position, then, or if it is minus x position, if you take the output as mod value, then both value will be same whether it is moved upwards by x amount or downwards by x amount. Okay, so we cannot distinguish the direction, because your position or your displacement is a vector quantity, is not it? So in order to characterize the displacement properly, only amplitude is not sufficient. We need to be aware about the direction also. Okay, so how to take care of the directions and how to understand the principle of LVDT in more detail, we will quickly see in this particular slide. Okay, so where linear variable differential transformer is used as a displacement sensor, and this is the practical diagram or image of this LVDT, as you can see over here, and this is encapsulated in that under metallic shielding. And here you can see this is the rod, or this is the basically the core which will be moving. And suppose similar to the potentiometer, if I want to estimate the object movement of this particular object, if I want to estimate the displacement x of this particular object, then simply I will connect this object to this core, and according to the displacement of the object, the core will move inside across this LVDT length, and accordingly the output voltage will change. So how it works, we will see here in more illustrative manner. Okay, so as I said, LVDT consists of one primary coil and two secondary coil, and the physical construction look like this one. So inside this block, the arrangement is like this. Okay, so where this is the movable core correspond to this one. This one is the movable core. Okay, and inside this, in the middle, we have the excitation coil or the primary coil, and in the two side of the primary coil, we have the pickup coil or the secondary coil. Okay, and what I said, the secondary coil are connected in series opposition. Okay, so when the movable core is equidistant located from both the secondary coil, that means when the displacement is zero, then the movable core will be located from that it will be located equidistant from both the secondary coil. So at zero position, the flux cutting at this secondary coil and flux cutting at this secondary coil, both will be what? Equal or different? If the distance from this to this and distance from this to this are same, so then flux cutting will be equal when the movable core is at null position or at x equal to 0. So then what will be the output voltage? Output voltage will be what?
0.
Very good. Because what we said, the secondary coil are connected in series opposition. So V1 minus V2, that will be 0. But when the movable core will move more towards this right side, so then either V1 will be more or V2 will be more, depending on whether the core is towards the right side secondary or left side secondary. Accordingly, your output voltage will be varying. Both the, if you take the absolute value, so then the output voltage amplitude as well as the this sign polarity, so both will change. Fine. So this is the actual schematic construction, and this is the actually for understanding purpose, we often represent the schematic in this fashion, where this is your that supply voltage here we apply, and this is the core, this is the secondary. So here if it is at middle position, then output will be 0. If it is towards S1, so then ES1 will be more, ES2 will be less. So overall output will be positive, since here if we consider ES1 minus ES2. Whereas if this core is towards S2, then ES2 will be more, ES1 will be less. So then output will be negative. Okay. Now here, so essentially we have understood that depending on this object displacement, the output voltage will change. Voltage means both the amplitude as well as polarity. Now, how to detect the output? Because how to detect the output? Because in transformer logic, you know that in order to make the transformer work, you have to apply AC voltage, right? Now, if it is moved towards positive side, so then the output voltage will be like this. If it is moved towards negative side, so suppose the output voltage will be like this. So what is the difference? If the core is moved plus x to upside, so then suppose the output waveform is like this. If it is moved same x amount in the lower side, then the output will be like this. So what is the difference between these two signal? What is the difference?
Phase difference.
Phase difference, 180-degree phase difference. So if you look at the waveform in some oscilloscope, then both will look like sinusoidal. Okay, so you will be confused whether it is positive or negative, because separately if you see both the signals separately, so then you cannot understand the phase, because in order to understand the phase, you have to compare it with respect to some reference value. So this particular concept is not that much convenient. Convenient means looking at waveform at the oscilloscope, that is not the convenient way. So what we essentially use as the signal conditioning element for this LVDT, we use some phase sensitive detector circuit along with some low pass filter. So what it will essentially do, it will convert, suppose if the voltage is like this, so then it will convert this to some plus VDC, and this one will be converted to something minus VDC like this. So that from the simple multimeter measurement itself, we can understand whether the displacement is positive or negative. So why we are saying all these things? Because displacement is a vector quantity. In order to understand the displacement, only amplitude, knowing the amplitude is not sufficient. We have to know about the direction also. So that's why in order to know the direction more conveniently, instead of looking at the waveform in the oscilloscope, we prefer the output should be positive for positive displacement, negative for negative displacement. That is more convenient to use. So that's why for LVDT, we have dedicated signal conditioning circuit required, which will detect the phase, and then that phase detector output will be fed to some low pass filter to give the DC output. Okay, so that is the salient signal conditioning circuits required for the LVDT. And what is the LVDT range? Typically, it can measure plus minus 0.25 millimeter to plus minus 25 centimeter. For a typical sensor of range plus minus 2.5 centimeter, the recommended VP means the primary side, the excitation AC voltage, what we are applying. Normally, the voltage amplitude is considered as 4 to 6 volt, and frequency is considered as around 5 kilohertz, and maximum nonlinearity is expressed as 1% of full scale division, plus minus 1% you can consider, right? And this is the characteristic. So your x-axis is the displacement, y-axis is the voltage, right? So AC characteristic means if you look at the waveform in AC, so then you can see this magnitude, only this absolute value, right? But DC characteristic means for positive displacement, positive output, negative displacement, negative output, right? So this dotted line correspond to the DC characteristic, which you are more convenient or you are more interested to see. So here, if this is the, this is your zero displacement, so this correspond to plus x displacement, this correspond to minus x displacement. So in this way, we can use the LVDT sensor to measure the displacement, both the amplitude as well as the direction. Okay, is it clear to everyone about the functionalities and principle of LVDT and the important signal conditioning elements required for this? Is it clear to all? Any doubt?
Sir, why such high frequency is needed?
Yes, very good. So basically that in order to make this system work, it can work in theoretically it should work in any frequency. So the typical value we have mentioned as 5 kilohertz, but here you can see this is the range is there 400 hertz to 50 kilohertz. That can be the applied excitation frequency. So you can apply any frequency in between these. And why we have these values? So these values are given by the manufacturer. That is so that the overall output will be, that means optimum, or the linear non-linearity will be within the range, or the other output factors. So like for example, that ideally at zero displacement my output should be 0 voltage, but practically you can see in the zero input also some finite voltage you can get from the LVDT output, that is called as the null voltage. So that value of null voltage will depend on these different frequency components, stray characteristic, and transformer property. So that's why keeping all those things in mind, the practical consideration point of view, these values are recommended. Yes. Someone.
Sir, I think high frequency is also preferred because at low frequencies, I think like the size of the circuit will increase, like it will design the low pass filter, the element size will increase.
Yeah, definitely. So that is also another factor. So that's why I'm saying that considering all the that practical applications or practical limitations in mind, these values are recommended. Okay. Now again you can understand that suppose if some static displacement is there, some static displacement is there. So suppose some 1 centimeter. So then accordingly you can get this type of voltage output, or for -1 centimeter you can get this voltage output, and then you feed it to the phase sensitive or the low pass filter, then you can get some plus VDC or minus VDC. But you can measure the dynamic displacement as well. Dynamic displacement means instead of some static displacement, suppose this object is vibrating, instead of some DC displacement, suppose this object is vibrating at some amplitude and some frequency. So then can someone tell me that if the input X is also vibrating, then in the output waveform, should there be any change, or the output will still look like this one? Any guess? The output, should it be function of that displacement frequency or not? Yes or no? Any guess?
So the
So the
amplitude of the
So
output
the
change.
amplitudes will also be sinusoidal. Amplitude.
So basically, this sinusoidal thing, what we are getting, what is the frequency of this one? When we have some static displacement, that frequency is completely similar as the supply voltage frequency, is not it? If I apply 1 kilohertz, so this will be also 1 kilohertz. But if my displacement is also varying at some other frequency, suppose 10 hertz my displacement is varying, then the output will be the modulating waveform, which will consist of this frequency term or component as well as this excitation frequency. So if overall the output will be modulated waveform. So are you aware about this modulated waveform? So this is something like this, where you can have this this type of modulating waveform where both high frequency and low frequency component will be. Then in order to remove this unwanted frequency, you may require some demodulator circuit as well, along with this phase sensitive detector. Okay, so anyway, so this is just for the information or understanding purpose, but the discussions what we are making, that these values are based considering the practical limitation in mind. Is it fine? Any doubts? If not, so then let us move forward to the next sensor. Yeah, someone is unmuted. Any question? Any doubts?
Sir, can you explain the graph in the previous page once again?
This graph?
Yes, sir.
Yes. So here what I said, that here two characteristic is shown. One is called as the AC characteristic, another is called as the DC characteristic. So AC characteristic means what we said initially, that this is your AC characteristic, is not it? That for both plus displacement, it will be sinusoidal. For minus displacement also, it will be sinusoidal. So their amplitude is same if the displacement is plus x or minus x, but the phase is different. So if we look at the AC characteristic, the amplitude will be same, but how to distinguish the phase, right? In order to distinguish, because AC characteristic means it will be having amplitude as well as the phase. So the amplitude point of view, both will be showing you same amplitude. If you go, suppose if this is the reference point, for plus x also it will show the characteristic is like this. For minus x, it will be showing characteristic like this. Obviously the phase difference will be there. Phase will be 0 degree and for this side and 180 degree for this side. So if you want to look at the AC characteristic, then both the amplitude as well as phase you need to know separately. So that is not that much convenient. So that's why we always go for the DC characteristic, where DC characteristic means plus displacement means this dotted line correspond to DC characteristic. So that means when the displacement is positive, then output is positive, plus y-axis. When the displacement is negative, output is negative, minus y-axis. So this is the difference between AC characteristic and DC characteristic, and DC characteristic is more preferable, which we are getting from this signal conditioning circuit output. Is it clear?
Yes, sir. Thank you, sir.
Okay. So next sensor is your accelerometer. Okay. So accelerometer, if we say, so then what it will measure? It will measure you the acceleration or the vibration, and it can measure you 1 axis, 2 axis, 3 axis like this. So depending on your requirement. And normally, also we have seen during our second order sensor system discussion that accelerometer can be, if you want to see the model of the accelerometer, it will be equivalent to your mass spring damper system, where one mass will be there. So this is your seismic mass, of when we call it, and then that mass will be connected through the spring or the damper to the vibrating object. So when this vibrating object, whose acceleration or whose vibration I want to measure, when this will be vibrating, then that vibration will be transferred to this mass spring damper system. That is the model of the accelerometer. So effectively, that displacement will be transferred to this mass spring damper system, and there will be relative displacement between this mass and this vibrating object displacement. And that relative displacement will be the function of the input acceleration or the input vibration. So by measuring the displacement of this mass spring damper system, we can tell what is my input acceleration or input vibration, right? So this is the schematic diagram, and here you can see this is the free body diagram. So here you have this mass is there, and in this case your x is shown as the upper side. So if x is going to the upper side, so then the spring restoration force Fk and damper restoration force Fb will acting downwards. And here this is your input acceleration, suppose m into a, mass into acceleration, that is the input force, and here you have this m into x double dot, that is the inertial force. So if you draw this, if we do the force balance equations here, so mx double dot plus lambda x dot plus kx equal to ma, that is the fundamental equations we will get, and from there we can derive the input output relationship. So here input will be a, acceleration, and output will be displacement x. So that's why x by a in Laplace domain, the expression is like this, where omega n denotes to root k by m, and zeta is the damping ratio that denotes the lambda by 2 root k. Okay. So here simply, actually, if you calculate the xs by as, it will be a function of m, lambda, k like this. But those m, lambda, k, we have combined them. Instead of m, lambda, k, instead of denoting them in using 3 parameters, we have denoted them using only 2 parameters. One is omega n and another is zeta. Obviously, omega n and zeta, they are function of k, lambda, and m. Now, naturally, you may say that why we have represented it in this fashion. We can write the transfer function in terms of m, lambda, k. Why these 2 parameters are there? That is because obviously if the parameters are more, then the calibration or the interpretation, that will be also relatively complex. So that's why instead of 3 parameter, we have judiciously combined them and representing the accelerometer only by 2 parameter, omega n and zeta. Okay, so that we can more conveniently understand the characteristic of the sensor, and this omega n and zeta are more conventionally established also, that how the natural frequency plays role in the system characteristic, how the damping ratio plays the role in the system characteristic. Those study are much more established. So that's why we are representing them using this combined parameter omega n and zeta. Anyway, so this is the equivalent diagram, and this particular schematic diagram or model is implemented while developing the accelerometer. So when we will be manufacturing the accelerometer, there also essentially we will be developing a mass spring damper system. Now naturally you may say that your A or acceleration is the input, and what is the output? We said x is the output, that is the displacement. Okay, but what we told, we want to get the output in electrical domain. Here again the logic is same. So input is acceleration, output is displacement, that is with respect to the raw sensor. Now that displacement we will be converting it into electrical parameter. What are the things in our hand? The same thing, resistance, capacitance, inductance. Right? So using either resistive, capacitive or inductive mechanism, we can convert the displacement into voltage. And so basically that voltage will be function of displacement. That displacement is a function of acceleration. So essentially from the voltage, we can calculate what is my input acceleration or unknown acceleration. Okay. Now, as I said, apart from this RLC, we have also another type of material which is called as the piezoelectric material. Piezoelectric, what type of properties it will give? When the piezoelectric material will be exposed to some vibration, it will produce you the electrical output. So in this accelerometer system, if you incorporate piezoelectric crystal here, so then from the piezoelectric crystal directly you can get the electrical output as well. So these are some of the transduction mechanism. Now, when we will discuss about the miniaturized sensors, so there we will illustrate in more detail how the fabrication of these accelerometers are done, how the integrations with respect to the circuits are done, and all those aspects. Okay. Now coming to the applications. So accelerometer finds enormous applications. Already we have seen the application of accelerometer in airbag system, in our electronic stability control, and so on. So those essentially come under the automotive, which includes monitoring vehicle tilt, roll, skidding, impact, vibration, along with the stability control, airbag, anti-lock braking system, and so on. Also, we can find its application in aerospace, inertial navigation, unmanned vehicle, in sports or gaming, monitor athlete performance, joystick, then personal electronics gadgets like cell phone, digital device, in security point of view also for motion and vibration detection, in industrial application also for machine health monitoring, we can use the accelerometer. And finally, in robotics also, for example, for self-balancing purpose, we can use the accelerometer. So this is just in smartphone, we have the sensors already we have seen, in joystick, robot, or in the smart band, which includes the biomedical aspects. So in that type of smart band also, the inertial sensors like accelerometers are incorporated. Okay. So this is about the accelerometer principle and the applications. And then here we are showing some commercial accelerometer example. So this is the analog device manufactured by analog device. So here also we can see mass spring damper system. That accelerations will be measured in terms of electrical output. So basically, mostly in commercial accelerometer system, the capacitance mechanism is used. So basically, the displacement what we are getting from the accelerometer, that is converted into capacitance, and capacitance is converted into voltage. So this is the schematic diagram of this that you can find in the data sheet of this analog device accelerometer as well. So here this is that raw sensor where you can see this is the spring. Okay, so this is the moving frame or the mass, and here we have some beams, and these beams act as the capacitor electrode. Okay, so when this particular mass spring damper systems will be vibrating, the gap between these plates will be changing, and that gap change means capacitance, because capacitance we know that for parallel plate capacitance, if I have two electrode, so then what is your parallel plate capacitance? C equals to epsilon naught epsilon r A by D, right? Where A is the overlap area and D is the gap between these two electrodes, right? So epsilon naught is the space permittivity and epsilon r is the relative dielectric permittivity of this medium. So if AR is the dielectric medium, so then obviously epsilon r will be simply 1. Now, if you're depending on the vibration, if the gap changes, so D changes, then effectively your C changes, and that C change you can measure using some dedicated circuit. So if you look at the functional block diagram of this accelerometer, you can essentially see that this is your actual sensor, differential sensors, that is the actual accelerometer. Apart from that, in this block, it will include the excitation signal, then you have the demodulator, then you have the filter, some timing generator circuits, and so on. And from here, you are getting the final electrical output. So that electrical output will be the function of that capacitance, and that capacitance will be a function of the displacement, and the displacement is a function of your acceleration, right? So basically, the acceleration A is converted into X, or basically delta A is converted into delta X, then delta X is converted into delta C, and delta C is converted into delta V. So that is the flow. And finally, from this delta V, we are back calculating or estimating what is my delta A. Now this is again another accelerometer. So this is the another analog ADXL 50 accelerometer is there. So here you can see inside this IC itself, you have the sensor is there. Apart from the sensor, you have the circuit part is also there, like carrier generation, oscillator, buffer, demodulator. So all the circuit components are also inbuilt together. And this is a small IC, and inside a small IC itself, so many sensor circuits are integrated together. And this is the example of airbag, where this type of accelerometers are deployed. Right? Another recent development is there in this accelerometer based sensor, which is called as this particular IC, which is MPU 6050 IC, which is called as the MPU 6050 IC. Fine. So this inside this IC, this is the complete chip, and this is the small board, and inside this small board, this is the actual IC. And inside this small IC, hardly it can be less than 2 centimeter cross 2 centimeter, this dimension. And inside this small dimensions, your accelerometer, gyroscope, temperature sensor, so many sensors are integrated together along with their circuits. And this is the functional block diagram of this particular IC, where in addition to the 3-axis accelerometer, 3-axis gyroscope, and 3-axis magnetometer, it includes the temperature sensor, the digital motion processor, and other signal conditioning block. So essentially, you have got the flavor that sensor not only means the only physical sensor, rather it includes the dedicated signal conditioning or interfacing circuits in order to develop the complete sensor system. Okay, so that from the sensor system, the electrical output what we will be getting, that will be the function of my input or unknown, that quantity which we are interested to measure. Okay, so you can understand the importance of that learning about the sensors, their working principles, along with their interfacing aspect. Okay, so this is about the accelerometer. This is also coming under the motion sensor. Is it clear to everyone? Any question?
Sir,
Yes.
sir,
Yes.
what are Bessel's filter?
Yes. So Bessel filter, that is basically we are aware about that low pass filter, high pass filter, band pass filter, band reject filter, like this. Okay. So Bessel filter is some that special type of filter that expression is there depending on their performance, that and these are coming from the name of the persons who has invented like this. So like there is some Butterworth filter, so where one special type of approximation or expression is used to develop the filter logic. Similarly, for Bessel filter also, a specific type of that filter expression are used based on the person who has developed this. And filter means, so suppose if I talk about the low pass filter, so low pass filter means frequency versus magnitude, right? So low pass filter means from 0 frequency to this frequency it will pass, and other frequency it will attenuate. Now the performance of the filter, like how much attenuation is there, what should be the noise in this pass band, what should be the noise in the stop band. So depending on that, different type of filter expressions are there. So similar to that, the Bessel filter is there, which is having a specific type of performance, and among each of the filters, they are having their relative advantage, disadvantage like this. Okay.
Sir.
Yes.
So what are those unit forcing cell and unit sensing cell in the like analog devices sensor?
Yeah. So yeah. So here unit forcing cell, sensing unit cell, like actually this further details of this structure principles. So those we will discuss when we will talk about the MEMS based sensor development. But just for your reference purpose, so here, as I said, so suppose if I take this one, so then what is the zoom version? So this is the reference frame, and it is like this. Okay. So when the reference frame is moving, depending on the vibration, so then what will happen? This middle plate will be moving. Okay. Whereas the fixed plates, the top and bottom, they are fixed, they are not moving. Only the middle plate is moving. Accordingly, the D is varying between this upper plate and lower plate. So in one plate, the capacitance across this top and middle, if the increases between top and middle, so for middle and bottom, it will be decreasing. So one side gap will increase, another side gap will decrease. So accordingly, the one side capacitance will increase, another side capacitance will decrease. So differential capacitance, that we are converting it into voltage using the dedicated circuit. So this is for the sensing purpose. Unit sensing cell it is written, right? So similar to that, you have n number of cell. You have n number of cell. To increase the overall sensitivity, like NC, it will be multiplied with n. Now, what about this forcing cell? Forcing cell means when we want to use the sensor in closed loop, when we want to use the sensor in closed loop, then the role of forcing cell will come into the picture. So what this forcing cell will do? Basically, this force, when if I want to use this sensor in open loop means when I am applying some particular input, accordingly the gap is changing, accordingly the capacitance is changing. That is straightforward open loop. And from that capacitance or the voltage, I am calculating what is my acceleration. But in closed loop, what happens? In closed loop, there we apply another feedback force we apply to keep this sensor at balanced position. That feedback force we apply using this forcing cell. So if the acceleration is applied upward direction, so then this forcing cell will move the sensor in lower direction to keep it at balanced position. That is in closed loop operation. So then naturally you may say that if it is moved X amount upward side, and from the feedback mechanism, if I move it downwards to the X side, so then what is the point of using the sensor? The point is, in that case, the sensor from the sensing cell, we will not measure the output. Then this feedback force will give us the measurement of your applied acceleration. That means in that case, when we are using it in a closed loop fashion, then we are not interested to measure this capacitance change in the sensing cell, because there essentially we will try to pull it back to the move null positions by this feedback force. In that case, how much feedback force is required to move it to the null position, that feedback force will give you the measurement of the acceleration. Okay, so these details we will further discuss during our that actual all the that sensor construction principle and so on with respect to the MEMS application. Okay, is it fine?
Okay.
Yeah. Okay, just quickly, if we see the animation, so then maybe your concept will be more clear. Just quickly see this. Wait a minute. Just a second. So let me open this animation link. Yes. So if you just see this, can you see the screen?
Yes, sir. Yes, sir.
So here you can see this is the mass and these are the springs, and the orange color is the proof mass and some beams are attached to this, and the other green color beams, they are fixed. So when some acceleration is applied, so then this middle mass along with the orange beams are moving, and accordingly the gap between these orange beams and the green beams, they are changing. One side is increasing, another side decreasing, and that will give you the differential capacitance. One side capacitance will increase, another side decrease, right? And then these are connected to the circuits to convert the differential capacitance into voltage. Okay, so is it more clear now?
Yes, sir. Yes, sir.
So coming to the next type of sensor, which is our gyroscope, which is the gyroscope. So that is again another inertial sensor. This particular gyroscope is used to measure the angular rate. Okay? It is used to measure the rate of rotation along three axis. That is the angular velocity or angular rate, which is more that conventionally denoted by roll, yaw, and pitch. Okay. So they use vibrating mechanical element to sense rotation. And here the basic principle is transfer of energy between two vibrating resonators caused by Coriolis acceleration. So we'll illustrate them. So suppose you can see this frame XYZ. Okay. Now suppose you are some platform is rotating. Okay. Suppose some platform is rotating along Z axis. Some platform is rotating along Z axis, and you are standing on that platform. Okay. Now, standing on that platform, if you throw one stone along y-axis, for example, with velocity v, what I said, you are standing on a rotating platform. That platform is rotating along z-axis with omega rpm, and then on that platform, standing on that platform, you are throwing one stone along y-axis, and the stone velocity is v. Then depending on this omega and depending on this velocity, depending on their cross product, v cross omega, a force will be developed which will be perpendicular to both y and z axis. And obviously that means along x axis one force will be developed, that will be the cross product of velocity v and omega, that is rpm. And because of that Coriolis force, that force is called as the Coriolis force. Because of that, the stone which you have thrown along y-axis, that will experience an extra force along x-axis, and because of that, the stone cannot move directly in parallel to y-axis. Rather, its motion will get deviated. Why? Because of the Coriolis force experienced by the stone, and that Coriolis force will be function of omega cross b. This particular basic logic is exploited to develop the gyroscope. If you see the practical example, like gardening, in garden, if you water your plants, okay, so watering of the plant in garden, then suppose you are holding the pipe across which the water is flowing along some axis, if you consider along the forward direction, and then if you rotate your hands along z axis, if you rotate, then the water, in that case the water will be resembling to the particle or the stone which will be moving at some velocity v, and you are rotating your hand along another z axis with some omega. So because of the cross product of omega and v, the water will feel another Coriolis force which will be perpendicular to both z and y axis, and accordingly because of that force, the trajectories of the water, that will get varied. So how this simple logic or simple property of this Coriolis force is being exploited to gyroscope, so that we will see in tomorrow morning. Okay. So till now, if anyone is having any doubts, please feel free to ask me. Any
Sir,
question?
Sir, in the Coriolis force like expression, like in the slide, why it is 2 times V cross omega?
Huh?
Sir, in the can you like
Yeah.
present the
Yes.
slide of the
So
Coriolis
very
force?
good. Yeah. So that is 2 cross actually that effective that it has been found that the force what has been that is proportional to V cross omega.
Yes, sir,
That is
in the
proportional to
like
V cross
why
omega.
it is
So
2 times
that
V cross omega? The
yes,
formula
yes.
here.
So that is proportional to V cross omega, and the proportional constant is found as 2. So that is because of its in that Coriolis nature itself. So if you look at the Coriolis expression, so there it is written that proportional to V cross omega, and that constant that proportionality factor has been found as 2. Okay.
Okay,
We will
sir.
illustrate on this tomorrow further. So quickly to see who are there. Pranav Shukla, are you there?